Hello everyone and welcome to another session of Digital Redays. My name is Son and I will moderate this webinar today. The topic of today's session is ICeGaN in a critical conduction mode Totem-Pole PFC. Our speaker today is Carlos Bada, who is working at Cambridge GaN Devices. Before we start with the webinar, I would like to give you some more information. First of all, you will be muted during the webinar. This means that you cannot ask us questions via your microphone, but you have the opportunity to ask your questions into the chat, and then after the presentation, it will be about 30 minutes long, Carlos will answer them in a short Q&A session. If you're unable to answer all your questions live within this time, Carlos will answer them via email in the next days. So last information from my side, you will all receive the link to the presentation as well as to the recording in the next days via email. So now I will hand over to Carlos and I wish an exciting webinar.
Good morning, afternoon, evening, everyone. Thank you all for attending this webinar, and many thanks in particular to Würth Elektronik to give us this opportunity. I am Carlos Toyos Bada. I am a senior application engineer here in CED. This is the agenda for today. The main goal for me today is to present you to our Totem-Pole PFC evaluation board that we have developed with our 55 milliohm ICeGaN device. You can see the evaluation board on the picture here. Briefly, I will introduce CED for those who haven't heard from us yet, and then I will start talking about the trends in the adapter market. So adapters nowadays require higher power, higher density, higher efficiency, and Totem-Pole PFC is a topology that is more efficient than the boost. So I will briefly touch this point. And then I move on to talk about the Totem-Pole PFC operation, the critical conduction mode, and the continuous conduction mode operation, what is more suitable for our 350 watts Totem-Pole PFC. And of course, I will give you an overview of the ICeGaN benefits in this topology. Finally, I will present the evaluation board test results, and at the end of this webinar, I will show you the TG portfolio, what products we have, and also I will mention a couple of evaluation boards that you might be interested. CG is a young company. We are based in the UK. Our headquarters and the main R&D site is in Cambridge in the UK. We have now different offices around the world, and we have experienced a significant growth in the last 3 years. So we are more than 60 employees, and we have many patent applications right now. And let me tell you that knowledge and innovation is at the core of the company, because the company is spun off from the University of Cambridge. And our mission is to develop and commercialize GaN-based power devices and ICs for the next generation of power supplies and power applications, to make an impact and make a better and more sustainable world. The market for low power adapters below, let's say 350 watts, is demanding more efficiency, more power, and more power density. So I think you might, many of you know that the USB PD 3.1 increase the power, the nominal power to 240 watts. And there are applications like laptops that required more than 300 watts, and also some other applications with multiple outputs to charge different loads and different gadgets. And all these power adapters, the consumer wanted to be portable and lightweight. And on the other hand, international standards and certifications are making the efficiency and the low power consumption limits tougher and tighter, and even adding some new limits. For example, in the past, I think the external power supplies, the limits were only for full load, and now there's an increasing trend that there will be limits for average efficiency, and there's also limits for efficiency and 10% load to minimize the losses when power supplies work at light load. You can see here on the left our chart that I made. So in average, the efficiency increase in the last 10 years in power adapters is about 4%, and the power density has almost doubled. And in this slide, you can see generalizations of the topology that you might find at different power ratings and different power densities. So for low power supplies that below 75 watts, when PFC is not required, you will find that flyback is very common, and above 75 watts, you will have two stages: one AC/DC stage, which provide power factor, and then the DC/DC stage that lower the voltage to the right output voltage and provide isolation. In this range, most PFCs commonly used as a PFC stage, and the DC/DC stage implemented with flyback flavor or ILC if more power density is needed. When you are above 240 watts, then bridgeless PFC has started to be very interesting, and Totem-Pole PFC is one of the most common topologies that can provide good power rating and good power density. And why is that? Is because the standard boost PFC, the traditional boost PFC, has a diode bridge in the input to rectify the mains, but this is the major source of loss in a boost PFC. So if we want to increase efficiency and if we want to increase power density, we have to get rid of this bridge, and we need a bridgeless PFC. And there are many different topologies, many different bridgeless PFC topologies, but the Totem-Pole seems to be a really good solution for a high efficiency and power density. Only uses 4 power devices, and it has only one inductor. So it's a really good candidate for substituting, for replacing the boost PFC at 300 watts ish. You can see here on the right, the Totem-Pole has 2 legs. So the slow leg that switches at 50 or 60 hertz, which is the mains frequency, is implemented with MOSFETs, and the fast leg, which switches at 10 of hundreds of kilohertz, that is implemented usually with wide band gap devices like silicon carbide GaN. In this case, of course, we use our 55 milliohm ICeGaN, and I will show you later what the benefits of the ICeGaN is in this topology. I'll quickly go through the Totem-Pole PFC operation. The Totem-Pole is just a boost PFC. So you have the AC mains, and then you are rectifying and increasing the voltage. You will end up with an output voltage that is between 380 volts, between 380 volts or 400 volts, roughly. So on the positive AC cycle, the low side MOSFET is on, the high side MOSFET is off. And the low side ICeGaN is the equivalent of the active switch in the boost PFC, and the high side device is equivalent to the diode in a boost PFC. On the negative cycle, the operation of all the devices are pretty much inverted. And in this case, the high side MOSFET is on, low side MOSFET is off, and high side MOSFET is, the high side ICeGaN is the equivalent of the active switch in a boost PFC, and the low side ICeGaN is the equivalent of the diode of the boost. And what current mode operation is best for 350 watts PFC stage? In general, there are two different operation techniques to operate our PFC: continuous mode and critical conduction mode. Generally speaking, continuous mode is more common for high power levels, about 300 or 350 watts. And critical conduction mode is actually not good for higher power. And this is because peak currents will be too high, and it would lead to a very high inductor flux. And also you can imagine that we will have excessive noise, and we will that required a huge filter. So critical conduction mode for higher powers is impractical, and I don't think nobody use that unless you have some interleave topology. On the other hand, critical conduction mode is an excellent choice for low power levels under 350, and this is because the PFC inductor has a smaller inductor value and has also a smaller size, and which is excellent news for power density. Another benefit of this critical conduction mode is that switching losses are lower than in continuous conduction mode, thanks to the zero current switching and zero voltage or valley switching that actually depends on the input voltage. Here on the critical conduction mode illustration, you can see the switching operation during the AC positive cycle. The low side device on the fast leg turns on. The inductor charges up, then turns off, and there's a small dead time, and then the high side device turns on, discharging the inductor current until you can see that it reaches zero. Then the high side device turns off at zero current. At this point, you can see that there's a resonance between the PFC inductor and the parasitic capacitance of the midpoint, which is effectively the drain of the low side device. Thanks to this resonance, most controllers turn on the low side device, and at the lowest voltage point, with input voltages below half of the output voltage. Actually the voltage across the drain is actually zero. So this is why it's called zero voltage switching. So for when you work in low line, you will have zero voltage switching. When you work in high line, the valley switch won't be 0, but it will be certainly smaller than 400 volts. And if you want to design a Totem-Pole PFC that operates in continuous conduction mode, you cannot use a silicon MOSFET, even a silicon superjunction MOSFET, on the fast leg, and this is because the body diode recovery losses. So the MOSFET had the body diode, and these losses would be a major source of loss, and the devices will get really hot, and the system will be very inefficient. In that case, we said that the critical conduction mode is better than the continuous conduction mode for higher efficiency and better power density up to 350 watts. But the current on the PFC inductor reset back to 0, so we don't have we won't have the body diode recovery losses if you use MOSFET. So the critical conduction mode Totem-Pole PFC, you can use MOSFETs, but the ICeGaN outperforms silicon superjunction MOSFETs for the same RDS. The switching losses are minimized with 0 current switching and 0 voltage switching, but are not 0. And energy losses is still present in the switching transitions, and particularly when the converter operates higher frequencies. And higher frequency operation happens, for example, at high line operation, and also when you work at light load operation or at the no load operation during the burst mode packages. The ICeGaN is a GaN HEMT and is driven like a MOSFET. And it's driven like a MOSFET. So the parasitic capacitance and the gate charge of the ICeGaN is significantly lower than a MOSFET, but on the other hand, our ICeGaN is easy to drive. It's almost easier to drive than even a MOSFET. It's much simpler to drive than discrete GaN. I will touch this point in the next few slides. And here you have a comparison of 3 different silicon superjunction MOSFET competitors with similar RDS on our 55 milliohm part. You can see on the left that the energy stored in the parasitic output capacitance is much smaller in the ICeGaN. It is more linear, so you won't have the voltage tail during the switch at low voltage, when the silicon superjunction MOSFETs have very high capacitance. And on the right, you can see that the gate charge of our ICeGaN is about 20 times smaller than in the competitors. So that means that low switching energy loss increase high line, light load efficiency, and not low consumption. And with ICeGaN, you will have faster transitions, and also you will need a very strong driver due to the low gate charge. So I told you before that ICeGaN is very easy to drive. So the big advantage of ICeGaN with respect to other discrete GaN is that ICeGaN can be driven like a MOSFET, and there's not a complicated standard driver circuitry or dedicated drivers like other discrete GaN needs. You can drive ICeGaN using a standard driver and a driver that you use for a MOSFET. ICeGaN is effectively a GaN HEMT, but we have added in the chip some additional circuitry. So the gate voltage range is from 90 volts to 20 volts, and the gate threshold is 3 volts. And on top of that, and this is very interesting, the ICeGaN has an internal mil clamp. So when the device when the device turns off, the gate pull down to the source voltage, ensuring that the gate to source voltage is effectively 0. So during dB by dt transitions, the Miller current, the parasitic capacitance, the current generated during these transitions on the parasitic capacitance will flow through this internal switch instead of going to the external driver out of the external gate pin, and that minimizes burst turn-on events, and the parasitic inductance on the external gate line is actually less critical than using a discrete GaN. You have to, as you can see here, you have a BDD pin, so you have to provide voltage to the ICeGaN. To this BDD pin, you have to put something between 9 volts and 20 volts to activate all this internal circuitry. The good news is that if the device is not switching, the BDD does not take any current. So this enables actually applications to achieve very low, no-low power consumption. And this is a comparison of the external driving component that you need when you use ICeGaN or you use discrete GaN devices. So for our Totem-Pole PFC on the fast leg, we have 2 power devices. If you use ICeGaN, you only need 4 components, 2 resistors and 2 capacitors. So 1 resistor and one small SMD capacitor per ICeGaN. On the left is the standard circuit that you would need if you use a discrete GaN with a standard half-bridge driver. And in the middle, you can see that even using dedicated half-bridge driver for the discrete GaN with lower gate drive voltage, you need more external passive components compared to the ICeGaN solution. Also, as I mentioned earlier, thanks to the milliclamp, you have more flexibility to extend the gate PCB tracks, because the parasitic inductance in these tracks are almost irrelevant during the turn off, because the current will flow through the milliclamp. And just one slide to summarize all the ICeGaN advantages in the half bridge and in this fast leg of the Totem-Pole. So ICeGaN is a GaN HEMT, and so it has lower parasitic capacitance, lower gate charge that allows faster transition. It will have lower losses due to the lower energy waste during the switching, and also it will need a driver with high sinus or source capability. On the other hand, as I mentioned, ICeGaN is very easy to drive, so it's almost easier to drive than actually a MOSFET. So there's no need for negative drive, there's no need for external turn-off path, and only 2 external SMD components are required per ICeGaN, and it works well with traditional bootstrap half-bridge gate drivers IC. So there's plenty of choice. There's a lot of flexibility on here with ICeGaN. And And here I'm going to present the test results we have achieved with this evaluation board. So you will have on the right the evaluation board that we have developed here in CED. It's a 350 watts Totem-Pole PFC. You have the simplify schematic on the left, and you have the link here at the bottom of the slide. So later, I think you can access that later on if you have my presentation. So as I mentioned before, we're using the 55 million ICeGaN to have the best efficiency possible. The evaluation board has a main board and a daughter card, and the fast leg with the ICeGaN and the driver AC is implemented in this daughter card. And I'll take this slide as an opportunity to thank you both, because they have been very supportive, sending us components, and in fact the bill of material of this evaluation will have many components. You can spot the magnetics and the capacitors, and almost I think most of the S&D capacitors are from Würth Elektronik. This is how the top sample of the daughter card looks. You can see there the two ICeGaN, you can see the HV driver, the bootstrap circuitry, and also the connection pins. So as I said earlier, only two S&D components are required per ICeGaN, and you might wonder why we have designed the board with 4 ICeGaN. So the board has been designed for actually parallel operation, but you can simply populate a single device and use the rest as pretty much copper as a heatsink copper that helps the cooling the device. So this is the actual schematic from Altium, screenshots from Altium. As I mentioned several times, only 2 SMD components required per ICeGaN, and we use the same hybrid driver for the slow leg MOSFETs and for the ICeGaN. So if you are going to implement this in a power supply, you have the advantage that you can have the same part. You don't have to choose another hybrid driver. You can choose the same part for the ICeGaN and the slow leg MOSFETs. Here are some test results. This slide shows you the efficiency of this evaluation board and also the nodal power. So as you can see, the efficiency is very high, nearly touching 99%, and in some cases, peak efficiency very high. Average efficiency also is very high. As you can see, even the 10% efficiency at any input voltage are more than 97%. And of course, on the right, nodal power, very low values, which helps and gives some room for the DC-DC stage to comply with the international standards. So, Again, power factor and total harmonic distortion. Power factor, you can see, for example, at full power, the power factor is more than 95%, and we are achieving pretty much less than 10% of full load, and in most points all over the range. There's a couple of thermal images of the thermal operation. At nominal low line, we have approximately a delta of 40 degrees increase in the device. At obviously a high line is only 26, and the board doesn't require any heatsink. It runs well with any heatsink, thanks to the good efficiency. So that translates into less thermal stress. And finally, these are the devices we have at the moment. Stay tuned, because I think in the next few weeks maybe this will grow. And I highlighted here in yellow the device that we use for the 350 watts Totem-Pole PFC evaluation board. There's some other devices. You can see we have 130 milliohm devices with different packages, and also a 240 milliohm device. We have the H1 series and the H2 series. For the evaluation board, I used the H2 series, which is a little bit more advanced, because it has an integrate circuit that minimizes the current in the VDD pin, which this is not implemented in the H1 series. So if your application doesn't need to, or you don't care much about no low power, you can use the H1 series, as long as you provide some current to the VDD pin all the time. If you care about the no low power, if you are going to design a power supply with a very stringent no low power consumption, then I would suggest that you use the H2 series ICeGaN. And this is another two evaluation board that we have. And actually, one is an evaluation board, is a 350 watts LLC. This one uses also the 55 milliohm devices. And the second one is 300 watts critical conduction mode Totem-Pole PFC plus the Hybrid LLC. And it's a reference design. It's a very high density, high power density design. Everything is squeezed in a very small footprint, and it's a very low profile. So please double check. And this is the end of my presentation. I hope you enjoy my presentation, and yeah, thank you very much for attending this webinar. I'll be here for questions.
Yeah, thank you, Carlos, for your interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from the presentation today. Now you can download it on the right side. And then I would say we can start with the Q&A session. Yeah. Carlos, are you ready for the questions?
Yes, I am ready.
Perfect. Then, first question. What is the maximum dV/dt that the ICeGaN can handle?
Okay, so you can go and see our datasheet and to answer this question, but I can tell you it's about between 60. Well, the rise time is about 80 watts per nanosecond. Full time it's slightly slower, but about 60 watts per nanosecond.
Okay, thank you. Then next question. What is your opinion about the best package choice for the ICeGaN?
The package of the H1 and H2, I think, it's very slim. It has a good thermal part, so you can put a lot of thermal betas, and you can see that in our evaluation board in the total card. You can see that you can provide a lot of vias, and we have good power dissipation. Even as I said, we don't need a heatsink, and obviously it could be really nice to have like a top cycle device, but well, I cannot advance anything, but stay tuned in the future months.
Okay, thank you, Carlos. Then next question. Which value capacitor is recommended for the ICeGaN VDD pin?
It's about with H2 devices. The H2 devices doesn't take any current on the VDD pin, and also if the device is not switching and the Miller clamp is not on, it's still protected by the internal circuitry. So you need a very small capacitance, like 100 nanofarads, something like that. Yeah. If you use H1 devices, you might need a bigger capacitor. You have to calculate it depending on the current of the VDD pin, which is about 1.8 milliamps, and the worst case time that your device is not switching.
Okay, thank you. Then, next question. Why has PFC choke an aux winding, and why is an resistor in GND?
Right, good question. So usually for the critical conduction mode, to detect zero current switching, you need the aux winding, because the voltage on the winding changes when the current reaches zero. And the resistor on the ground, breaking the ground, is because it's needed for the controller that we are using in this particular evaluation board. But if you use another controller, or if you use a microcontroller, for instance, you don't need this resistor.
Okay, thank you. Then I would say we have time for one last question. What was the limit for the maximum power in this evaluation board, since the ICeGaN has such low case temperatures? Oh, sorry. Yeah,
it's okay. The maximum power of the board is 350 watts, and you can run it at even very low input line, 90 volts. So that is the hardest operation point, because at 90 volts full load, you have the highest input current. So yeah, it's worst operation point. But yeah, 350 watts all over the input range.
Okay, then one last question. Is there anything special about GDD devices which makes it easier to design for lower EMC emissions, or is the design process the same as for any other PFC, SPMPS design?
I think generally, saying EMC is difficult, but in ICeGaN, the turn-on can be controlled by the gate resistor. So you can control this turn-on and switching edge. And the turn-off is you have less flexibility. So it's the middle clamp which defines the speed of the switching. So yeah, the turn on, ICeGaN makes easier with just one resistor.
Okay, thank you. Then we are finished with the session. Thank you, Carlos, for your interesting presentation and also for the answers of the questions. If you have any questions, if you have any more questions, sorry, you can write in the chat and then Carlos will answer them via email in the next days. So thank you for your attention. I hope you enjoyed it, and hopefully we see us on our next Digital Days session. And then I would say thank you and goodbye.